Hi, welcome to this video on Recursive Algebraic Coloring Engine, a graph coloring library that allows to parallelize and efficiently run sparse kernels having data dependencies. In this video, I will briefly explain the motivation of this work in view of sparse matrix computations. We will discuss on data dependency problems that commonly arise in this field and associated difficulties in parallelizing these algorithms. We will then look into existing approaches to solve this kind of problems. Especially, we will focus on graph coloring methods. Then we will look into unexpected performance problems occurring during such computations. In order to resolve this problem, I will further introduce you a novel approach called Recursive Algebraic Coloring, or the RAC method. We will look into details and briefly discuss on how this method is formulated. I will then introduce you to a library called Recursive Algebraic Coloring Engine, the so-called RACE library, which implements the RAC method. Finally, we will look into the performance results we obtain using this approach and do some comparisons. So let's get started. Scientific simulations in various fields like structural mechanics, fluid dynamics, quantum physics, and so on starts with defining a problem. The next major step is mathematical modeling and discretization. The end result of this is a set of linear equations, which can be represented by a couple of vector and matrices. Commonly, the matrices that come up here are sparse, which means they have lots of zeros in them. One common optimization strategy is to save precious data storage and transfers by storing only non-zero entries in them. This is called a sparse matrix. All the further computations are then performed on this sparse matrix. There are various data storage formats for sparse matrices, and one of the most common format is called compressed row storage, the so-called CRS storage format. In this format, we store values of the matrix consecutively in the row major order. Now, due to this compression, as we lose the information on position of non-zeros, we use a column index array to determine the column position of each non-zero. And the position of row is determined by a row pointer which points to first elements in each row. On the left, we see a simple but widely used kernel, so-called SPMV or sparse matrix vector, which, as the name suggests, does multiplication of a sparse matrix and a vector. Each row of the matrix is computed one after the other until all the rows are finally processed. Now, if we want to parallelize this code and thus make it run faster by using the power of modern multi-core processors, we might think of shared memory parallelization schemes. Let's, for example, use here simple OpenMP pragma to accomplish this. Here, we insert the pragma in outer loop going over all rows. The rows then get distributed between the threads or cores that we currently have. This means if we have two threads, then in this case, thread 1 starts with working on the first row and thread 2 on fourth row. They process all the rows independent of each other until completion. With this SPMV algorithm, each thread reads matrix A and vector X and writes to a vector B. Note that although multiple threads can read from the same element of vector X, but it writes only to a single element of vector B. Since this parallelization of this kernel is as easy as that, it is also called embarrassingly parallel. All said now, we could further think to save more data storage and traffic. For example, in case of symmetric matrices, we could consider just storing either lower or upper triangular part of the matrix, since one is the transpose of the other. The same matrix vector multiplication, when storing only upper triangular part, would then look like this as seen here on the left. Now, this is called a SymSPMV. Here, we need to do a matrix vector multiplication for the upper part and a transpose matrix vector multiplication to account for the missing lower part of the matrix. Now, if we try to parallelize the kernel as done for SPMV, we see that we will soon run into a problem. Due to the indirect writes or stores on the vector B, which depends on the column index, it can happen both the threads write into the same entry of B. In this case, this occurs if two threads work on row having similar column entries. If you run this code as it is, you would end up in wrong results, as you can no more control whether each thread has seen the values updated by the other thread. Such kind of dependency is called a distance-to dependency. There is also one another common dependency called distance-1, where a similar but not so severe dependency exists. There are many kernels that have similar kind of dependencies. For example, iterative solvers like CuxMux, sparse matrix transpose vector having distance-2 dependencies, or solvers like Gauss-Seidel having distance-1 dependency, and so on. There exist approaches to solve this kind of problem. For example, one could use locks, which allow only one thread to write or update an element at the same time. But with this, one has to pay the price of serialization. Another approach is that each thread stores private copy of the vectors and updates only this private vector. At the end, results of all threads are combined with a reduction operator. Obviously, here one has to pay the price of extra data traffic. A relatively new approach is to store the matrix in a completely different storage format, like CSP or compressed sparse blocks, or another format called recursive sparse blocks. But this approach would need code rewriting or conversions. Most popular class of method for dealing with distance-1 dependent kernel is by reordering or permutation of the matrix. A common method used in this category is the so-called multicoloring. An extension of this method in regard of performance improvement is the so-called algebraic block multicoloring method. These approaches can also be extended for solving distance-2 dependencies. The basic idea of this class of method is to find rows that can be executed in parallel. In the case of distance-2 dependent kernels, we saw that problem arises due to threads working on rows having same column entries. One could then group rows that do not share any common column entries. This group is then called a color. For example, here if you notice red colored rows, they do not share any common column entries. And therefore, different threads can work in parallel within a color. Once a color is completed, the threads are synchronized and we start processing rows of the next color. So it would work something similar to this. So all the reds are done, and then the green colored rows are done in parallel, and then the blue colored rows. Algebraic block multicoloring extends this idea by first dividing the matrix into blocks and then applying coloring on top of these blocks. Threads then work in parallel between blocks of the same color. Now, as we have understood the basic principle of these methods, it is a good time to check the performance behavior of these methods. The following results were obtained for running the symmetric sparse matrix vector or the SIM-SPMV benchmarks using NLP-KKT 200 matrix, which is available publicly in Suite Sparse Matrix Collection. Here we have chosen a modern Intel Skylake architecture to do this benchmark. The plot shows performance of different methods in number of gigafloating point operations done in a second, or abbreviated as gigaflop per second. Here we compare multicoloring method, algebraic block multicoloring method, and Intel MKL implementation. Here we can easily observe ABMC, or the algebraic block multicoloring method, performs the best in this case. Since computing time is equivalent to energy and money, it's important to ask the question, are we actually at the limit or can we do better? Seeing this performance graph without any reference doesn't actually give you any insights. Therefore, we create a reference using performance model. Using performance model, we try to estimate an upper limit of the attainable performance. But how does it work? It's a fairly easy concept. Let's go to the street to find out. Let's assume there's a constant flow of cars or traffic throughout a street. Now we are interested to find out number of people transported through this road in a given time, which we denote as P. This could easily be calculated by estimating the amount of cars flowing per second and multiplying it with average number of occupants in a single car. In computers, it's not much different. If we consider cars as data transferred from main memory and occupants as floating point operations we do on this data, which means now P is floating point operations in a given time. The amount of data flowing per time is called bandwidth, which is fixed for a given architecture. And number of floating point operations done per data transfer is called intensity, I. This means performance P is nothing but bandwidth times intensity. The formula holds mainly for performance on an entire socket or chip for data-intensive streaming codes like we have in sparse kernels. This is the so-called roofline model. The only thing that is unknown in this performance equation is intensity, or the number of flops done per byte of data. This we can find by analyzing the code. Here, in the case of symmetric sparse matrix vector, we do 4 flops, 2 multiplication and 2 adds for each non-zero. This requires 8 bytes for the value of the matrix in case of doubles, 4 bytes for column entries that are stored in 32-bit integers, 16 times alpha byte for the B vector. Value 16 comes from 8 bytes to read and 8 bytes to write the value. The parameter alpha is the data locality or the reuse factor which comes from indirect aces of B, which depends on column indices of the matrix. Since the data once loaded from main memory is kept in fast but small caches for specific time, we might not sometimes need to load the same data again from main memory. But this heavily depends on sparsity pattern of the matrix and cache size of the hardware. Similarly, for the X vector, which we read, we need 8 times alpha bytes for every non-zero. Finally, we need 4 bytes once every row we process for reading the row pointer, which gives us this nice little expression for intensity. A lower limit for alpha value for symmetric sparse matrix vector can be obtained directly from measuring the data traffic of normal SPMB kernel, which is embarrassingly parallel. This can be typically done using tools like Liquid. The next unknown, the NNZR, is average number of non-zeros in a single row of the matrix. This can be easily calculated for a given matrix. For example, the NNZR value in our case is 14.3 and alpha value is 0.22. Furthermore, the actual data traffic can be further measured using Liquid tool. And now, if we compare with the ideal data traffic seen in the denominator of the intensity equation, we see that there is a positive deviation of all methods from the ideal case. This indicates there is some extra data traffic which we haven't accounted for. But let's now look into the actual performance. So once we have the intensity, we can easily calculate the performance by multiplying it with the bandwidth of the entire socket, which is 115 gigabytes per second in this case. Again, If we compare performance model with the actual performance we obtained for each method, we see that there is a significant deviation in performance from the model prediction, which is indicated with the bold red line. One of the major reasons for this deviation is basically due to increased data traffic, which we have already observed. And the cause for this can be understood by observing sparsity pattern of the matrix after coloring. Coloring has the tendency to increase the bandwidth and disperse the elements within the matrix, leading to bad access pattern on indirectly accessed vectors. For example, in this case, if we just observe access of vector B and assume we have a cache that can hold only say 8 elements, it can be seen for operating on red color itself, the entire B vector is accessed and there was no reuse within the color. By the time it comes to the next color, where it tries to reuse the elements in B, which was already loaded during the operation on red colored rows, it is already evicted from cache. And this needs to be loaded again from main memory. This causes an increase in alpha factor, which directly reflects in higher data transfers and consequently lowers performance. This can be seen as analogous to the case where only cars of one particular color are allowed to pass through the road for a certain time. And the rest of the cars nearby, which has a different color, have to go back and try once the current color cars have all gone through. Along with data traffic, there are other factors like synchronization costs and fault sharing that also contributes to performance degradation. The contribution of these factors depends on the matrix. Since with ABMC method, coloring is only applied to blocks and within blocks they have better data locality, the data transfers is lower and performance is higher compared to multicoloring. But still, we see with performance model there is some room for improvement. Now having in mind potential problems that could happen with coloring, we will formulate the recursive algebraic coloring method, which tries to alleviate some of these problems. The main objective we have here is to have good hardware efficiency. And in order to do that, we now understand that it is important to have lower alpha factor by preserving good data locality. Along with that, we have to try to reduce synchronization costs and at the same time have sufficient parallelism to support the hardware underneath. Furthermore, this has to be applicable on simple data formats like CRS. The recursive algebraic coloring method or the RAC method consists of 4 steps: the level construction, permutation, distance k coloring, and load balancing. At the end of 4 steps, if sufficient parallelism is not attained, we apply the steps in a recursive manner on selected subgraph of the matrix. To explain all the 4 steps, we use a simple sparse matrix related to a 2D 7-point stencil example. Any matrix can be represented with a graph. Graph basically shows the connectivity of the matrix. Formulation of the RAC method is done on the graph of the matrix. The sparsity pattern and graph of the matrix can be seen right over here. The first step in RAC method is level construction. It can be seen that the best permutation to increase data locality would be to keep the non-zero elements close to diagonal of the matrix. This was observed previously in the case of normal SPMV computation and has led to preprocessing of metrics by bandwidth reduction algorithms like breadth first search or reverse Kutilmäki. In this step, therefore, we do the same by applying breadth first search on the matrix or the graph, for example. In this process, we start with a vertex of the graph, which we assign as level 0. The next level comprises of all vertices that are connected to the vertices of previous level and which are not yet assigned a level. So level 1 comprises of all vertices having connection with level 0. Similarly, we can find all other levels of this graph. And in this case, we have 15 levels numbered 0 to 14. L of I here denotes ith level. This step can also be substituted with RCM instead of BFS, bandwidth reduction. Once the levels are constructed, we then permute the matrix according to the levels. So vertices of the graph now gets renumbered in the order of increasing level numbers. The procedure till here was similar to any bandwidth reduction algorithm. But since now we need to color the matrix, we need to store additional information of levels. This is done using a level pointer, which points to the first elements of each level. In the next step, using this level pointer, we do a distance k coloring. K is 1 in case of distance 1 dependent kernels like Gauss-Seidel, and 2 in case of distance 2 dependent kernels like symmetric sparse matrix vector or Kuxmax. One can prove that level I and level I plus or minus k plus j are distance k independent for all j greater than or equal to 1. This simply means for distance 1 coloring, if we leave a gap of at least one level between any two levels, these two levels are distance 1 independent. Similarly, in case of distance 2, a minimum gap of two levels should satisfy this criteria. For example, here you see one configuration which resolves distance 2 dependency, and here you see that we have two colors and we have grouped some levels together to form a level group, which we denote by T. So T of I means ith level group. Now, all the red colored level groups are independent of each other because they are separated by two levels formed by blue level groups between them. And similarly, blue level groups are independent of each other. Now, threads are assigned to level groups of a single color and they can operate in parallel. Once red colored level group is finished, it can move to the blue level groups. Since we haven't changed the permutation from the one prescribed by breadth first search or RCM, we have better data locality. It can also be seen that a single thread working serially within a level group which is formed of elements having strong connectivity or are close to each other. Currently, this method has a drawback of load imbalance. Because for instance, if you see level group 0 has only 3 vertices, while at the same time level group 4 has 13 vertices. Therefore, thread working on level group 0 will obviously finish its work faster and it would have relatively less amount of work. In order to fix this problem, as a final step, we do a load balancing scheme. The idea here is to plug in details from the hardware side like parallelism required and also bring in the concept of load balancing, that is to distribute equal amount of work for each thread, while at the same time satisfying the criteria for distance k coloring. For example, if the hardware just supports 5 threads, we could assign more threads to level groups having small number of vertices, so here, and at level groups where non-zeros are high, we try to maintain the same amount of non-zero as in other level groups and at the same time try to preserve distance k coloring requirement. This is the reason why we see level groups in middle over here consist of only 2 levels, which is the minimum required to attain distance 2 coloring. But now the question pops up. Since by this approach one has limited parallelism which depends on the total levels that we have, and as we approach the limit we have load balancing problem, so how could we resolve such problems? The answer to this is recursion. Here we select some level groups of the matrix and apply all the 4 steps on this level group to generate more parallelism. The choice of the level group is made by a global load balancing algorithm. It also determines how much parallelism a level group has to obtain. In general, this means for a given matrix, parallelism required determines the coloring configuration, and the recursion required. At the execution phase, threads working on level groups where recursion has been applied spawns more threads in a nested manner and executes this level group in parallel. For the example shown here in first step, all the red level groups are executed in parallel. Red level groups where recursion is applied spawns 2 threads and does first orange colored sub-level groups in parallel. Once the first color is done, it executes the next color within this red level group. As we see here, since we have almost twice as many vertices in the level groups where recursion is applied, the 2 subsweeps can be completed by 2 nested threads in the same time as the other threads complete the red level groups in parallel. Once all the elements in red level groups are processed, it moves to the next blue color and repeats the procedure. This is basically how the rack method works. Next, I will quickly introduce the race library that implements this rack method. Race library supports user in 2 phases, the pre-processing and the processing phase. In the pre-processing phase, user needs to provide the sparse matrix, specify the type of coloring he wants like distance 1 or distance 2, and specify the hardware settings like number of threads required and the pinning strategy to be used. The library then internally generates a tree which stores the information on the level groups at each stage of the recursion. It then gives out a permutation vector and user just needs to permute the matrix according to this vector. The race library also internally creates a pinned thread pool which can be later used in the processing stage. In the processing stage, user applies the kernel having dependency and its arguments. Library then executes the kernel in parallel using the internal tree and pinned thread pool it created in pre-processing phase. Having an implementation of the method, we can now study the performance behavior. First, we compare symmetric sparse matrix vector implementation of race against the performance model we introduced earlier. We choose a number of matrices from suit sparse matrix collection and some of the matrices from quantum physics field. In the first experiment, we use one socket of Intel Skylake architecture having 20 threads. The orange line corresponds to the performance obtained using race library. The performance predicted by performance model is shown in gray. In actual practice, the bandwidth varies a bit with the ratio of load to store streams. Therefore, the 2 lines shown for the performance model corresponds to the 2 extreme cases of bandwidth, load and copy respectively. From this plot, we see that the race implementation is close to the model in most of the cases, except for some pathological cases like crankseg1. One can also notice that the performance gain one has over normal sparse matrix vector computations. Similar plots are obtained for one socket of Intel Ivy Bridge architecture having 10 threads. Since here the bandwidth is lower than that of Skylake, you see that the performance and the performance model is lower than that of Skylake. The previous comparison of symmetric sparse matrix vector using different methods were as follows. Now with race, we get a decrease in data traffic and reach close to the performance model predictions. Comparisons with rest of the matrices on the Skylake architecture is shown here. In most of the cases, race has an upper hand followed by ABMC or algebraic block multicoloring, the MKL, Intel MKL implementation and the multicoloring method. Note that in all the cases, the matrices has been pre-processed with RCM to make a fair comparison. The matrices are ordered according to the number of rows, and one can see race has a bigger impact on larger matrices since here the alpha factor plays a much bigger role. Similar results can be seen for the Ivy Bridge architecture. Next, we show the performance of Cuxmark's iterative solver on Skylake architecture. The plain performance of this kernel is shown here. But for iterative solver, as reordering the rows also changes convergence, it's important to look at the convergence pattern. The spider plot gives the information on ratio of iteration each method needs compared to the serial execution. One can observe race method lies close to 1 in most of the cases and is comparable with ABMC method. Now, combining these two information together, one can get the actual time to solution for this iterative solver. On the screen, we see a plot of inverse time to solution for different matrices where we again see the benefit of race. From the performance studies, it can be seen that race has a performance advantage in most of the matrices. And in some cases, we could also obtain a speedup of 2 or more compared to other methods. In this video, we also see how performance modeling can be used as a helping tool to guide optimization. For more details on the RAC method and the race library, please visit SC18 ACM Student Research Competition poster session. Thank you.